Hey, we're going to go through mission synthesis. It's going to be more on how mission synthesis works than the software, but we will show some demonstrations in the software. Okay, so just an overview slide from SimCenter Test Lab. We're in the SimCenter group, and the SimCenter group also consists of CAE software. We really like to do simulation and test together. So we have 1D modeling, SimCenter Amazon, SimCenter 3D, and CFD, SimCenter CFD. We try to make all these work together. We really believe the best approach to engineering is combined simulation and test. So what do we want to do with mission synthesis? What we want to do is create an equivalent damage test on a shaker that represents the field vibration or damage. And the reason we want to do that is we don't want things like this to happen. Generally, it's not too good when your missile doesn't fire. Ideally, we're trying to replicate the load seen in the field on an electrodynamic shaker. So what we're going to do is cover some background fatigue principles, and I think it will help when we get into calculating some of these functions that are specific to mission synthesis. So fatigue all got started in 1842. There was a big crash in Versailles, and they sent somebody out to investigate it. And what the revelation from there was that the cyclic stress can be as important or more important than the static. So we assume that you design it right towards the static part, right? That at that time they designed the train correct for the static. What they didn't account for is the axle rolls, there's a cyclical load, and that accumulated damage over time and fell. So this started fatigue off. Static strength fells in one cycle. Cyclical fatigue, which we're going to be talking about, developing tests that replicate cyclical fatigue, is a gradual degradation and eventual failure that occurs under loads which vary with time, and obviously they have to be below this static stress limit. Because static, you fell one time. So we're going to need a couple of things to relate this stress or strain we measure to fatigue. And one's going to be an SN curve. So an SN curve tells us how many cycles to failure we have from a constant amplitude load. So if I go to 100,000 cycles, I fail at this stress level. And these material curves are created with machines, so they cycle at a constant stress until they get to failure. And they count the cycles, and generally they do multiple parts at loads, because over any given stress level, there'll be a distribution of numbers of cycles to failure. Even with smooth machine specimens, we cycle at a given stress level, they all don't fail at exactly the same time. So there's some variation in them. Now in this SN curve, we have some different regions. Infinite life, this is where if we keep the stress below this level, it never accumulates damage. So a lot of engines operate in this area. They design to infinite life. And then we have a plastic region. This is where we have a non-linear relationship between stress and strain. This is what we also call low cycle fatigue. So we're designing a part that 10,000 is a rough number, but operate in the low cycle range. High stresses will usually have plasticity here. The region we're going to focus on is this elastic high cycle fatigue region. So now we have a linear relationship between stress and strain. And this is where a lot of our components operate in. They're not designed to last forever, which is down here. Some of the reasons engine manufacturers do that is it's hard to count cycles. If something spins at 6,000 or 7,000 RPM, cycles can accumulate very quickly. So it's hard to get a good count sometimes. So we have an SN curve, cycles to failure, and we have a stress level. Now we need to figure out how to calculate damage. And this is going to be important because one of the functions we're going to talk about is called a fatigue damage spectrum, and it will use this as part of coming up with that function. It'll use Miner's rule. So we want to introduce it so you know what it is. So Miner's rule is a way to calculate damage. So what we do is we take a cycle, here's 2 cycles, and we have an amplitude of that cycle, and we go over to the SN curve. What's an SN curve? It's cycles to failure from a constant amplitude load test. So we go down here and we read how many cycles to failure at that stress level. We have 2 cycles in our waveform, it's 6 to failure. So it's just a simple damage model, 2 divided by 6 or 0.33 damage. Now, if we add another cycle at a higher amplitude, if it's a higher amplitude, it'll be lower cycles to failure. So this is 2 cycles at 4. And since Miner's rule is a linear damage model, we simply can add the 0.33 to the 0.5 damage to get 0.83. The theory is that the part actually fails at 1. So then at this case, we wouldn't meet failure, and we could add another cycle, and then we would see above 1 and have failure. Okay, so that's Miner's rule. Here it is in another fancy mathematical formula. Also, just give credit where credit is due. We always call it Miner's rule, but it's really technically, I think, Palmgren-Miner's rule. So we know what an SN curve. That's going to help us calculate damage once we have a stress level. And we know how damage is accumulated. It's a linear model. So mission synthesis. There's 2 documents that this presentation is taken from. The MIL Standard 810 has a lot on developing tests. And then there's a test specification development by Christian Lillane. Most of our software is patterned after that text. It's a 5-part series. It goes sign, random, shock, FDS, and specification development. So when we're designing these tests, they're for electrodynamic shakers or sometimes hydraulic shakers. And typically there's 4 types of tests. Well, 5 combined modes, but time waveform, where we're replicating a time waveform, generally done on hydraulic shakers, generally lower in frequency range. There's swept sign testing, random testing, and shock testing. And then there's also something called combined modes, where we combine random and sign testing. Either random with fixed sign, swept sign, or random with fixed narrowband random or fixed sweeping random. What we're going to cover is developing sign and random tests. We will cover just briefly, we can calculate a fatigue damage spectrum, which we'll talk about later, from a combined modes test. The other thing I may not have mentioned is not only do we want to replicate the field damage, but we want to replicate it in a faster manner. If in the field it's 1,000 hours, we want to develop a 5-hour or 10-hour test to get that damage and replicate the same failure mode. Most of the time, we end up synthesizing a random test profile. So random is a very common mode. And again, we're in the elastic region, so high cycle fatigue. Just in case you haven't seen it, what we're going to do is we're going to put our components on top of a shaker. The 3 here, the upper left and the ones on the bottom are electrodynamic shakers, and the one on the right is a hydraulic shaker. Just to give you an idea, typical frequency ranges on these electrodynamic shakers are up to 2,000. On the hydraulic, 200 would be higher. Advantage of hydraulic shakers is we can put some preload on it and we can get a lot of stroke displacement. These are more displacement limited. Generally, 5 hertz is really low, and I mainly only see it in sign testing, and I see it in qualification, not so much the durability type testing. But 5 is generally the lower end here. Here's our problem statement. Component is mounted on a vibrating structure. So this is a component test. It's not like a full frame or a full vehicle that we put on one of those big hydraulic rigs. We're talking about a component that we mount on something. We mount this component on a structure that vibrates it. And we don't know what happens inside that structure. Sometimes we don't even know where the component will fail. We generally have an idea what's our weakest link. Also, it's either very time consuming or difficult to take this input and monitor what's inside that box to model it. So what we're going to do is we're going to use a hypothetical system. We're going to use a base input into the structure, and we're going to make a model of the structure to kind of predict what's going on inside. And this is specified a lot in this Lillane, one of the references in the presentation, how to do this in details. Now, what we really need for the test, to design this test, is we need the input into the structure, because that's what we're going to design. This is a PCB. This PCB is mounted in some black box. We're going to put that in a system, and when we test it, it's going to be put on a shaker. So mission synthesis is a base excitation. We need to have the energy going into the structure, and that energy is acceleration, because that's what we're going to control on the shaker. We're going to control accelerometers. Now, if at all possible, it's good to take some data on the structure itself so you can get an idea of fixtures. We like to mount it with the same mounting impedance that it is in the structure, but a lot of times that it is in the field, that's not possible. So generally we'll have different boundary conditions on the shaker. And if you put an accelerometer on the structure, then you can have an idea of whether you're actually over testing or not. So if possible, take some response measurements on the structure itself. Also, these shakers are single axis. We're going to develop a single axis test in 3 directions. That's just where we're at. There are some multi-axle electrodynamic shakers, but they're very rare. The common thing is single axis, and we would develop an XYZ. On the hydraulic, we see a lot more multi-axis test rigs. Again, what we're going to control, what we're going to develop the profile for is this base excitation. We're going to control off this head expander. And the idea is we're going to develop a profile that says, if this part survives this on the shaker, it's going to survive it in the field. Mission synthesis process. So why do we do mission synthesis? Well, we want to derive a shaker profile, but the other part people use this for is they will compare the severity of one test to another. The other thing I've seen is I've worked with some suppliers who will get profiles they have to test to from different OEMs. They want to develop a test that meets the requirements of all their customers. I've seen it used for that as well. We're deriving specs and we're comparing the severity. A lot of times people use standards, so maybe we've taken some field measurements and we want to see how the field measurements compare to the standards. So how are we going to do that? Well, we could just use a standard, but we're not going to do that. We're going to take some data, measure some input accelerations, we're going to calculate some functions, and we're going to synthesize a profile on electrodynamic shaker test. And that's what we're going to go through in detail. So here is our process. We're going to define the mission. We're going to take some data. We're going to analyze that data into these functions: shock response spectrum, maximum response spectrum, fatigue damage spectrum. Then once we get that for each of our loading environments, we're going to combine that into one overall life profile, FDS, MRS, SRS, and then we're going to synthesize an accelerated test profile from that. That's our process. So we'll go through each one of these steps in a little more detail. To me, this is the hardest part because you have to know the loading environments that your product sees over the life. So you need to break the life of the product down into X number of loading environments in this case and you need to know how much time it spends in each one of those loading environments. Because we're going to get the damage from each one of these scaled to the time, and then we're going to combine them all together. This could be the hardest part. The data we take is fairly simple, but you really have to know your product and how it's used. If you already have a proving ground schedule, then this is a lot easier because you can take that proving ground schedule data and you can say, okay, how much do they run at track A, track B, track C, track D, however many they have, and then you can develop this profile. But if you're in a new market, this can be the hardest part. For the automotives, they have proving ground schedules they've had for years. So if you're going to put something on the car, they got a pretty good idea of what the loading profile is. When we quantify loading environments, we want to qualify them as series or parallel. Think of series events as and. I got to run this and this and this and this. And parallel events as an or. I got to run this or this. The reason that's important is when we get to the process of combining these, we will combine these environments either as ands or ors in different ways. Typical or events are like the United States or Brazil, train or ship, or truck or ship, highway or air or something. The data we take again, is pretty straightforward. It's the input into the structure. So if it's this rear view mirror, we want to get here. Now, if you were to have a bigger structure with maybe multiple attachment points to where it was mounted, you could then take multiple input accelerometers, and then we could envelope across there to get the worst case. Generally, we're going to do a triax because remember, we're going to synthesize 3 single axis tests, an XYZ type test. We're going to measure acceleration. If possible, it's good to have some measurements on the part itself, just so you can see what's going on, especially when we get into the lab. We can input into the process. If we can't get a measurement, we really like time, because when we calculate SRS from time, we don't have to make assumptions. But if we can't get time data, and if one of our environments was, say, a mil standard, we could input a PSD into the system. But you're going to see that when we input PSDs, we have to make some assumptions about the amplitude distribution at a frequency line, and that assumption isn't always correct, and I can show you how that comes out in some data. And remember, we want the input into the structure. That's our must-have. Nice to have is on the structure itself. So now we've defined the mission, we got our loading environments, we've taken all our data. Now we're going to calculate some functions: shock response, maximum response, and fatigue damage spectrum. So our accelerometer is our input, and it represents this base excitation. Then we're going to model our structure as a bunch of spring mass damper systems. This has frequency 1, 2, 3, 4, 5, and we're going to specify some attributes of that spring mass damper. So we're doing a base excitation, because remember, I'm going to put this part on a shaker, on the head expander. So model the unknown component as a singled off system. We got K, C, and M. Basically, the K and M, square root of K over M, that's the frequency. And the damping, we're going to call it the Q factor. Q is a measure of damping. Natural frequency is varied, so we're going to test at various frequencies. The Q is constant over the whole thing, so we're going to choose a Q. Typically, I see 10 used a lot. So you can look at these systems as almost filters. We don't get into the convolution integral in detail, but we're going to use this Duhamel convolution to represent this filter and get the output from this base input. So what this is going to allow us to do, this is going to be our base processing to calculate the shock response, maximum response, and fatigue damage spectrum. This model is going to be used for all of them. Let's go over this little movie on the shock response. So we're going to build our model here. We have our input. We have our different frequencies, our different spring mass dampers. Then we're going to apply our base excitation. We're going to measure the output. And if it's an SRS, we're typically, I don't know if you saw we did a webinar on the SRS, but the dimension is going to be the max acceleration out. So here's a condensed form of that. I take time in. Now, most people, when you say SRS, they think shock. But in this case, the SRS is calculated on a lap around the track or every one of your loading environments. And it's going to be the peak output response, peak output acceleration of that accelerometer. Now, the MRS, the only difference between the MRS and the SRS is that the MRS has a PSD as an input. So we're going from the frequency domain. If I already have a shaker profile and I want to calculate MRS on it, I would input that into the system. I could also calculate an FDS, as you'll see in the next slide. The maximum response, we call it the maximum response. And if you look in literature, in the internet, you also might see extreme response spectrum. Again, it's peak acceleration based on a PSD input. Now, the problem with PSDs is at each line, we don't really know what the amplitude distribution is. So we're going to assume a Gaussian distribution. Sometimes that's good, sometimes that's not so good. Okay, and I'll show you how to see it in the data. So at each thing, we're going to make an assumption. And that's why if we can use time as the input, it's a little more robust. Now we get to the fatigue damage spectrum. The front part is exactly the same, except for output out of that integral, I can get, if you've looked at the SRS presentation, you can get relative displacement as an output. It's a dimension you can set for an SRS. We take that relative displacement, we have an SN curve and Miner's rule, and we can calculate. So we take the relative displacement trace out of this filter. That's the difference between the mass and the base. And then we have a time trace after this filter, and we can do rain flow counting and use Miner's rule. And then we can get the damage at each of those filter frequencies, or each of the frequencies that we specify. And this is a tool for assessing the fatigue damage potential of an input vibration. And it's displacement based. So the other two are acceleration. From here on out, whether it's an MRS or an SRS, and if you use our software, we're always going to call it an MRS, okay? So the MRS is the MRS in shock response spectrum, and the FDS is the FDS. When you calculate these, there's going to be certain things that you have to specify. And we're not going to cover this in too much detail, but on the right here, we can also calculate these on combined modes tests. So if you wanted to get an FDS on a sign on random or random on random, you can do that here. We're going to focus on this standard application. So what are we going to need? We're going to need a Q factor. We're going to need a Wöhler exponent. This we'll talk about briefly, but it's totally optional. Then we're going to need to know the min and max frequency and the frequency resolution. These are the frequencies of our spring mass damper system. We can do that either log or linear. We select the excitation, time, or PSD. If it's time, we need the number of repeats. And if it's PSD, we need how long it has to survive in that environment. If it's swept sign, we'd also need the number of replays. In the software, this is a little bit confusing. You'll see a K and an A. I've really never seen it used, but it's there to actually calibrate this acceleration to a relative stress. It's not really needed in the process because we're doing a relative damage comparison. But if you wanted to try to get a more precise damage comparison at one spectral line or one filter frequency, you could use this. What you can't do is you can't take those lines and sum them up to get one damage number across that FDS if you did this. If you want to do a strain life or a stress life, you could convert your acceleration to strain, then you should just do the damage calculation in the time domain, not go through the FDS and then use this and then sum the lines. Okay, the quality factor, typically we see 10, it's 5% damping ratio. And we want to talk a little bit more about the B. The B is really important. The B is the slope of the SN curve. The B affects how much we need to raise the amplitude of the PSD to get a certain time reduction. Remember, the only way in the frequency domain to accelerate a test is to increase the amplitude. That's the bad news, because that's going to make us ask some questions about, did we raise the amplitude too much? In the time domain, just for your information, we have ways to accelerate the test without increasing the amplitude. But in the frequency domain, we're always going to increase the amplitude. So here it gives you some guidance from literature, electronics 6.4, NATO standard, aluminum 8. The default in our software is 5. B is really important. You're going to use it when you calculate an FDS, and you're going to use the same value when you synthesize a profile. We've calculated all these functions. We're going to add them together. Really simple. If the situations are parallel, you always take the worst case. You always envelope the situations, whether it's an MRS or an FDS. Remember, like I said, MRS includes the SRSs too. We're lumping those in. The only difference is time input or frequency input. If they're in series, we're still going to envelope the MRS. So we're kind of get a worst case MRS. For the FDS, if it's in series, we got to do track A and B and C and D. Then we're going to sum it. So we're going to accumulate the damage, which kind of makes sense. After this process, we're going to have one life profile MRS and one life profile FDS. And there's a couple of factors we can take into account. So one is the uncertainty factor. And what the uncertainty factor does, it gives us a way to account for how confident we are in the hour, in that the hour that we measured, but it's really got to survive 1,000 hours. How confident are we that that 1 hour represents the 1,000 hours? And you can do a user-defined factor, a constant factor based on some materials, or you can do a variable factor. So if you took 20 runs, you could see how consistent the runs are. I don't see this one used as much, but it's a way to account for how confident you are that the loads you put into the system actually represent the total time that you use it for. The test factor is used more often, I see, and the test factor says, I'm trying to predict a population performance from a small sample test. It's simple. The more samples I test, the lower the level of the profile. If I test one sample, I got to test to a higher rate to be equally as confident as if I tested 5 samples. So this takes into account a factor that adjusts for how many samples you're testing. Typically, we don't test one sample. They test 3 or 5 or more samples. The more samples you test, the lower level you can test to for each of them to pass to be confident about your population performance. So that's the test factor. We can synthesize a profile. Here's the fancy math behind the profile. What you need to know is that thing in orange is the test duration. You're not going to change the B. You're not going to change any other settings. The only knob you have to turn here is this time, test duration. So you're going to set a test duration. Now, here's where it gets hard. Let's say it's supposed to survive 1,000 hours, and you can say, I want to do a 10-minute test. Well, it's probably going to be so high, it's not going to be realistic. You can say whatever you want. And then you've got to determine whether you over-accelerated the test. And that's the real engineering judgment in the mission synthesis or any frequency domain process. So here we go. Of assuming we've applied the test factor and we applied the uncertainty factor already. So we take our FDS and we're going to synthesize either a PSD or SWEP sign. And all we're going to specify is the test time. So now we have a life profile MRS and a life profile FDS. We bring it in here and say it's 440 hours and we want to do a 44-hour test. We type in 44 hours and it calculates a PSD that was the same damage as that life profile. From that test PSD, we then calculate an MRS. So now we got an MRS of the life profile that we came into this block with, and we have an MRS of the test profile. And then we're going to compare those, the MRS to life to test. Remember, the only way to accelerate the test is to increase the amplitude, so our MRS should go up. We're going to make sure it hasn't gone up by, these are qualitative rules of thumb, no more than 1.5, maybe 2 max. We'll talk about some caveats. If it has, if it's gone up too much, then we're going to increase the test time and resynthesize. If we're okay, we send it to the shaker lab. The only knob we have to turn here is the test time. Here are some graphical examples. So I have my life profile, my test profile, and what they're trying to get here is a limit shock. Not a lot of people have this, but if you have a limit shock, you can put it on this plot. If you're anywhere near your limit shock on your high cycle fatigue, bad things are going to happen. What we want is to get acceleration, we want the MRS of the accelerated test to be higher, but not too high. In general, rule of thumb is 1.5 to 2. I'll have a slide on that. If for some reason this MRS is anywhere near the shock or above it, you've way over accelerated the test and you need to back off on the time.
Real quick question. Where does the SRS limit shock profile come from?
It could come from a really severe event, like a pothole or something like that. An event, a drop, like when they do, say, transportation studies, they also do drop tests separately. If you're accelerating your transportation test, you're making your own, you're not using a standard. If you're accelerating so the MRS is near the drop test, then you're going way too high. I don't often see people have this limit shock, but if you have it, it's just another data point, because there's a lot of judgment in how much you can accelerate it. Everybody's greedy. We all want to replicate the damage in as fast a manner as possible. Testing time is money, and we want to reproduce the failure mode. But if we over accelerate, then we can get a lot of false negatives that they don't fail in the field. There's two methods for developing a frequency domain test. The one we've spent our time on is called mission synthesis. But there's another one called PSD enveloping. And PSD enveloping is used a lot in aerospace, and it's used on stationary random signals. So a stationary signal means that if you had 100 seconds of data and you took the RMS every second, it would stay pretty much constant. So stationary random signals. It also uses the theory that the damage is proportional to the RMS acceleration. We take our shaker profile and a random controller, we always know the RMS, that's our damage level. Okay, it's proportional to that. Mission synthesis says damage is proportional to displacement. Since we use rainflow counting in Miner's rule, we can account for transient data that's not the same RMS. If you have 200 seconds of data and 5 seconds are really bad, it'll be weighted accordingly. The slope of the SN curve in both of these, B, affects the acceleration. I will caution you, be careful about B and K. They're easy to mess up. So we can rearrange, we can take Basquin's formula. Basquin's formula is a formula for an SN curve. The number of cycles to failure, that's like our test time. And the stress level, that's like our RMS level. We always kind of want to keep in mind this number. The ultimate strength divided by the endurance limit. The ultimate strength from fatigue is strength where we fail in one cycle, and the endurance limit is the level. If cycles don't go above that, we don't generate any damage. The ultimate strength divided by the endurance limit is about 2, approximately 2, for steels. This is a generalization. So we rearrange Basquin's law, and we can calculate these functions called an exaggeration factor and a time reduction factor. So PSD enveloping just takes the RMS level and it slides it up and down the SN curve to get a time reduction. That's all it does, but I think it can really help us evaluate, because we can take our shaker profile and we can apply this technique to calculate what is a reasonable time reduction factor. So what Lalane has done in his book, it's a table taken from the book, is he's held the exaggeration factor constant, ratio of RMSs, let the slope of the SN curve change, and calculated a time reduction factor. 2 is a very aggressive exaggeration factor. If you think of, I'm running 5G RMS on a shaker and now I'm going to run 10, if you just experience that, that's a big change. This is a fairly big change. So I generally look at this. So if I can expect maybe a factor of 10. Now these are rule of thumb, and what it depends on is where you start on the SN curve. So if I start at here, I know the ratio between here and the endurance limit is 2. So I had better not be multiplying that RMS by 2, or I'm really could be overcooking. If we're already in the high cycle rate with our base measurements, we're up here above the endurance limit, generally multiplying by factors by 1.1, 1.2. So 1.5 is pretty aggressive. Now I have worked with clients that have had vibrations that were down here and they want to develop an accelerated test. And this was something on a manufacturing floor and it was a PCB. In that case, we could accelerate by a lot. So it really depends how much you can accelerate these factors by where you are on the curve. But most, if you take a proving ground schedule, I guarantee you're going to be in this high cycle fatigue. Okay, so this is a nice table. Now what we're going to do is we're going to plot these MRS of my life. This is my limit shock, just made that up. But typically I have my MRS of my life profile and test profile. And I'm going to look at this and say, is it a 2 is really high? So I look through this whole range and say, oh my God, that's 2. I need to back up. So in this case, I tried to do a 1-shift test, an 8-hour test from 440 hours. So I'd probably, instead of doing that 8-hour test, I'd probably do a 44-hour test. Now notice that this doesn't have a constant value between it. Notice when I get over here, the ratio is a lot closer. This is the difference between calculating the MRS with time data and calculating the MRS with a PSD. To make matters even more confusing, I've seen data where I know I accelerated the test, the RMS level went way up, and the green line in some ranges was below the black line, or the accelerated line didn't go up. It confused the heck out of me. Just be advised that's possible. It has to do with the MRS from a PSD based on that amplitude distribution being Gaussian. Right now, I don't know how to get around that other than using engineering judgment. The software doesn't have a different PDF type distribution that you can use.
One other question came up here. Do you just compare the GRMS values of RMS of accelerated tests to life profile to determine over acceleration?
No, I use my GRMS to look for something that I could expect using this. So I can calculate my life profile RMS and my accelerated and see kind of what my exaggeration factors are. What I typically use to see if I've over accelerated is this. I calculate the MRS of my test profile, compare it to my life profile, and I want to make sure, again, this is just a qualitative rule of thumb, 1.5. I think 1.5 is high. Again, it all depends. All this analysis depends on where we start on this SN curve. If we're way up here, if our life profile comes up way up here, we may not be able to accelerate that much. Now, what I'm going to do is I'm going to jump over and just show you kind of a quick example in some software. So what we have here is we have an air cleaner. It's attached to a truck frame, and we have 1 lap of data, and that it's got to survive 4,800 laps, which is 1,200 test miles, 4,800 hours. So that's the design criteria. So I pop over to mission synthesis. I'll just start over from the basics. I'll delete that and I'll browse over there, pull it in, and now I'm going to enter the repetition factor as 4,800. And then I'm going to go over here and I have some extra pre-processing if I want to do it, but I'm going to pull up my compute MRS FRS. I'll leave this at 5. I'm not going to worry about trying to get to this actual stress because it's relative. I've got time excitation and I've got 4,800 repetitions. This is pretty mathematical intensive, so that I calculate fast, I'm only going to go 5 to 200 hertz. Convolution integral took more time. If I go out to 2000. So here, if I had combined modes and I wanted to calculate an FDS, I could do that here. I could override my repetition factors. Down here is pretty self-explanatory. If I had multiple environments, in this case, I only have 1 lap around the track, but if I had 4 tracks, here I could do all my enveloping and summing. If I have a PSD, you can calculate a confidence level on it. Here, uncertainty factor and test factor. So if I'm going to use these factors, they're optional, then I need to apply them to both the MRS and the FRS. So I could calculate a uncertainty factor, either user defined, constant, or variable, and I can a test factor. Choose the distribution. These values come a lot from text. I have a confidence level, and then I put a number of tests. Number of tests is the number of samples I'm going to test of this profile. Just to let you know what it does, if I have 2, the test factor is 2.26. If I have 5 and I click off that, it goes down. And that'll be a scalar that I scale this FDS by. After I get those all prepped, then I can go over here and calculate excitation. PSD, linear sine, log sine, sweep, mostly we do a PSD. The only knob I have to turn is this. So I can put an 8-hour test in here, and this part goes really fast, calculate it. And then I could also say, okay, I'm going to calculate a 44-hour test because we know this total is 440. And if I wanted to calculate a life profile test, I could say 440. Then I could go here and I can compare my 3 tests. So obviously, as the time goes, you can see the PSD between the life profile and the 44-hour test and the 8-hour test. The MRSs should change and the FDSs should be roughly the same. I got some plots, so I'm going to switch to a different section that kind of go through this so we can go over some of the plots. Just to get an idea of what our data looks like. So the green is the data that we did. It's not stationary, so this was a lap around the track. So if I would have done PSD enveloping, I would have focused just on this section of the track for 322 seconds, and I would have over tested. The red line is my RMS value, it's not stationary. So when you get a case like this, you really need to use mission synthesis. The other thing I did is I just calculated different methods of PSD. So here I did a peak hold. So what if I peaked hold? If I peak hold that, I had an 8.37 GRMS. If I took the average, I had 1.29. So this is an under, this is an over. And here's my 44-hour test at 5.69. My MRS comparison, this is what we saw in the plot. This was with the 8-hour test. So I would go with the 44-hour test. The real engineering judgment here is in how much of an acceleration rate. And knowing where you're at on the SN curve can help by what you can expect for a time reduction factor. The slope affects how much we have to increase the amplitude to get a given time reduction. It's called mission synthesis. If you have tokens, it's 24 tokens to run. Thank you. Well, send me an email if you have any questions or you'd like to go through this on your data or try it out or whatever.